All right, well, thanks everybody for coming. I'm Patrick Dolan. I'm a senior machine learning engineer at FlightAware. Today I'll be talking about a project I worked on where we needed to scale XGBoost to train on a really large data set and how Ray made that really easy for us. And I'll discuss some tips and tricks I learned along the way that helped speed up our model training. So this isn't the sexy LLM use case you hear about all day, but if you've been around machine learning a while, you know XGBoost is still a workhorse that a lot of people use, and it's pretty good at solving a lot of problems. So it's nice to know how to scale it. So what we'll talk about is FlightAware, who we are, what we do, the use case in this project, which was predicting which runway an airplane is going to arrive on, how distributed XGBoost works on Ray, what bottlenecks you start to run into, and then how to overcome some of them or at least speed them up. Then in the end, I'll talk about some of the actual metrics and costs of stuff. So FlightAware started in 2005 as kind of a hobby project for private pilots and aviation enthusiasts, tracking planes all over the world, just seeing where they go, see your friends on a flight, you want to know where the plane is. So it grew into this whole worldwide thing. We're tracking airlines, cargo, military, charter, anything that's publicly trackable, we track it. So it fuses data from over 50 sources into a unified feed of basically what's happening with aircraft all over the world as soon as they turn their equipment on. So that includes schedules we get from airlines, governmental authorities like FAA, Eurocontrol, ADS-B, which is automatic dependent surveillance broadcast, which is pretty much required in all controlled airspace now. They send their GPS back to air traffic control, but you can also just pick it up on the airwaves yourself. And so we have a network of volunteers around the world that feed that data back to us. So we basically have petabytes of historical data available for both analytics and machine learning. So the team I'm on, we come up with product ideas and experiments based on all this data that we have. So the use case here, predicting arrival runways. And so fundamentally, for this project, we wanted to see if we could build a model that predicted what airplane the runway was likely to get assigned to when it landed at its destination. So we evaluated some different neural network architectures, but ultimately landed on XGBoost since it was a tabular data set. It turns out XGBoost is just so good at this, it's pretty hard to tune a neural network to get better performance. It's also really efficient to train it on a CPU. So you can train it on a GPU, but it doesn't really worth the trade-off since GPUs are generally pretty expensive compared to CPUs. So this diagram is an example of SFO airport. So you have like 4 physical runways, but the plane can come from either direction. So you actually have 8 logical runways that have their own unique identifiers. So this problem can get pretty complex when you have airplanes getting assigned to like parallel runways and things like that. But the model trains on historical data that we have collected about what's happened in the past, what runways they were assigned, where the planes were, what the weather was, data about the runways, positioning of things, air traffic patterns, all of that. And so kind of one of the questions we wanted to answer was, when we were investigating this, is whether a model could actually learn this, because it's a classification problem, but the classes mean different things at every airport. And so we wanted to see, could the model discern, like if this one variable is different, that these classes mean completely different things. And it turns out they can. The XGBoost does pretty well at this. So it assigns a category from 0 to 20, basically, a classification problem for which runway we think, and then we map that from a physical runway into what runway that is for human beings, right? So maybe 13 left is a 0 here at DFW, 13 right's a 1, so on and so forth. So this is an example of a Baton Rouge to Dallas-Fort Worth flight where it starts off, you see it had one prediction about the runway, and then as the airplane got closer, the model decided it was more confident in a different runway. So it's continually updating its prediction throughout the flight and streaming that back, and it's exposed to our customers via APIs. So how do we do this? We basically start with the raw data that we have from all these different feeds. It gets stored in text formats with like key value pairs, and then we sync all that to Amazon S3. We use Spark and Amazon EMR. So we filter, we transform, we join it all together into these big data frames, and then we spit out our feature vector, which currently has 263 features that go into each training example. So that gets written into a data lake of Parquet files that lives in Amazon S3. And those are the source data that we use to train the model. So we need to shuttle all of that data into a training cluster, and it goes way beyond the limits of a single machine. So now we have to solve the problem of working out how do we distribute this, since we decided XGBoost worked pretty well. So that leads me into distributed XGBoost on Ray. And so there's a few different options for distributing XGBoost training. There's Ray, there's Dask, there's Spark, there's Kubernetes, and I think there's a few others. And we looked at several of them, and we came to the conclusion that Ray was the best one because it's really simple to use, it's platform agnostic, it's stable, it has a really nice UI, it has metrics, it has insights. You can just go look like how much of the cluster is being utilized, how much network is going in, what are all the graphs. And we also had some other projects we're working on where we needed like distributed data loading, and we were seeing what Ray Data was doing with the neural network training and some of the other projects. So XGBoost Ray is an open source library, and we use open source Ray. It's pretty well supported. It's actively developed. Its API is like almost identical to just native XGBoost. In fact, if you've used XGBoost, this probably looks pretty familiar to you, but this is like the Ray stuff that's on top of it. So one of the core pieces of the API is that it's got this Ray D-matrix object, which is the analog to XGBoost native D-matrix. So this is just basically all the training examples in this giant matrix. It wants to load it into memory, and then it does all the tree calculation from there. So it supports both centralized and decentralized, or distributed, data loading. So in the centralized one, that's where you have like a pandas data frame or some big like NumPy array or one big CSV file. But what we use is called distributed data loading. So basically the capability is the remote actors, like the head node figures out where all the files are, and then it distributes them among all the workers. So the workers are only loading the data that they need to calculate their portion of the solution. So that could be a local disk, could be NFS mount, HDFS, S3, can do all that sort of stuff. It also supports distributed data frames. So you could do Modin or Dask or Ray datasets now. When I created this project, Ray datasets this was like over a year ago, so they made tons of progress. We may eventually switch to Ray datasets, but for the time being, we're just using this underlying. So Ray data does underline this, but we're not using that API layer directly. It just kind of happens all for free for us. So this is just an example of some of the parameters you can pass into it. It looks really similar to XGBoost training. So on the left, you have XGBoost parameters, so their objective is just a multi-class classification. It's evaluating on log loss and error. The tree method, the histogram method, this is a lot faster for CPUs. They invented this originally, I think, for the GPUs, but then I think LightGBM was the first one to take it and make it CPU-based using the same algorithm. So they got notorious for being really fast at training, and then eventually XGBoost brought that algorithm over as well. And then on the right, you have the Ray parameters. So those are separately configured. So you can say, I want this many actors. I want each one to have this many CPUs. Then, of course, you have the elastic training options that you've seen in some of these other presentations. So you can say, like, I will allow this many actors to fail or restart. And so what this allows you to do is start to use spot instances. So it can checkpoint, it can recover, it can do all that stuff. And then you basically just call this training function, tell it where the data is, what the parameters are. And our code is really not much more complicated than this. It's just like really simple. So this is a high-level diagram of like how distributed training works in XGBoost. So it shards that training set of all those files, figures out where to send them, and it uses this all-reduce function called Rabbit, which is the reliable all-reduce broadcast interface. So it integrates the results from each worker into the global solution, and then using this, you can basically put as many workers as you want. You could have hundreds or thousands. We've never needed to go anywhere near that crazy with it, but like Ray makes that possible, and that's what's pretty amazing is we're not doing any distributed computing stuff in our code. We're just telling it where the data is, that there is a cluster, and it just does it. So bottlenecks. So there are some things that you can do to speed this up. So for example, now we can load all our data from the source. Each worker is only loading the data it needs. But by default, it's going to do that over the S3 APIs, which are HTTPS, and those can sometimes be not so fast. If you have gigabytes of data to load, then that can become a bottleneck. It can take hours to like load that data from S3 into the memory of your instances. So like here's an example of just default S3 APIs. It was doing about 16 megabytes a second. So you can see how that can quickly become a bottleneck. The second one is memory. So the way it works by default is XGBoost wants the whole training data set in memory. There are some experimental options to do kind of batch loading, but they say it's not like officially production ready, at least the last time I checked. But anyway, this turns out to be really fast anyway if you can fit it into memory, because you don't have to do all those transformations on the fly. But the peak memory usage can exceed about 3 times the size of your actual data set because of some conversions that happen in there. So XGBoost, if you're running it on a 64-bit system, it will convert all those integers and floating points into 64-bit. And so you want the lowest precision that's practical, because it's going to load some of your data from the source into memory, and then it's going to convert it into this D matrix. And it's going to do both of these things in memory at the same time. And so the XGBoost array docs, they show you some small like toy examples, but I'll show you the real ones that we use. So we have 263 numeric inputs, some are integers, some are floats. An average day's worth is 17 million examples. So that's 4.47 billion data points. So in 64-bit storage, that ends up being about 36 gigabytes per day. And if you train it 6 months of data at a time, that's 6.4 terabytes. And so what we found, or what I found in like actually training this thing and trying to size the cluster right, is it can eat about twice that memory. So we've often stood up clusters that are roughly 12 terabytes of memory. And the last one is disk speed. So this is a little less critical than the other ones, but it does matter, right? So remember that each worker in the cluster, they have their own object store that they write data to. That needs to be fast. Most of the cloud instances now have solid state drives, so this is less of a concern. But if they write to shared memory, but if it starts overflowing, that's going to go to disk. So there's some help you can give it there when that sort of thing starts happening. So now let's talk about how we can speed some of those things up. So our objective here is to get the training data from the cloud into memory as quickly as possible while not burning a bunch of expensive EC2 time. So network file systems turn out to be a pretty good solution here, because you can load those ahead of time. You don't have to do it while the expensive training cluster is up. So Amazon has a few solutions for this. EFS, Elastic File Store, is a common one that implements the NFS protocol, but there's actually a better one that's highly optimized for like machine learning and data processing and analytics. And so it's FSX for Lustre, and it's basically a POSIX compliant file system that you can set up ahead of time, and it'll basically map an S3, some location inside S3 to the mount on the file system. And so that has that has microsecond latency, gigabits per second of throughput, and millions of IOPS. So it's really fast, and it basically acts as a high-performance cache that appears as a Linux file system. So you can really maximize throughput here. So this table shows you kind of how fast that thing can go. So it scales with the size and the type of the volume. I usually use the Scratch instances because we don't really need it to be blazing fast, paying as much as possible. But even the Scratch ones, you get 200 megabytes per second for every terabyte of storage. And for that particular class, I think 9.6 terabytes is the maximum you can use. So that's a baseline of 1,920 megabytes a second, or about 2 gigabytes a second. And it can burst up to 12 gigabytes a second. So if you provision the persistent volumes, you get a high availability on top of that. So if you want that volume to just live around for a while and you want your data there, maybe you want to train multiple times or you want to do different stuff with it, that's an option. That baseline on that is, I think, 2.6 gigabytes, or no, 2,600 megabytes per second per terabyte. So it's about 13 times faster than the Scratch, which is what we use. So you can really go full throttle on this thing if you need to, which is really cool. This is an example of what it takes to set one up. It's really simple. This is just the AWS CLI command. So you're telling it you want this Lustre file system, how much, SSD type, which subnets and region, tags. You can also, so you can see there, I'm mapping that particular path in the S3 bucket and that's going to be mounted in the root file system when we mount it to the instance. So this is pretty easy. You can add data compression if you want to. In our case, it didn't really help any because we have compressed Parquet files. So compressing it again would save you some disk space, but we weren't using all 9.6 terabytes. So there's really no real reason to add that overhead for us. So this is an example of how you would mount it. So like if you had your own cluster and you were doing that with YAML, this is how you might do it. So you basically just create this /fsx folder or wherever you want, then you do this mount command. This basically comes straight out of the AWS docs. And one of the best tricks here is you can pre-populate this file system. So by default, it's like a write-through cache. So it's going to, when you request a file, it's going to load it from S3, it's going to put it on the disk, and then it's going to give it to you. And so you can go in here ahead of time with like a really cheap instance, like a T2 medium or something, and you can just issue these commands. Like this command would go to that directory, find everything in September that's a Parquet file. And this LFS HSM restore, so this also comes from the AWS docs. It's like a little hidden trick that's in there. That'll basically go ahead and take all the data from S3 and put it on that disk. And so that way it's as close as possible to the instance when you need it. And this is really fast. This loaded about 40 gigabytes of data, which is about a month of Parquet data for us in about 2 minutes. And we can load 6 months of training data in under 20 minutes. So when you think about what we showed before, where it's like just downloading all the stuff over S3 APIs while the EC2 is just sitting there burning the clock, this we can do. We're not burning any EC2 time. We just load it all into this really fast cache disk. And then when we do spin up the cluster, we mount it. All this data is there immediately. So memory is the next thing, right? We calculated earlier we're going to potentially need terabytes of memory to load and transform this into that native XGBoost D matrix. So for smaller jobs, the R6 family is pretty nice. It's high memory compared to the CPU, but they only go up to 1 terabyte. So you end up having a whole bunch of these together. Not only does it get expensive, but then you have like a lot of cross-network talk. So what I ended up using, or what we use most of the time, is these X2I instances. So there's different types of high memory instances. This one has a really high memory to CPU ratio. They can support up to 4 terabytes per instance. The network transfer rate's up to 100 gigabits, and it comes with some extra NVMe drives attached to it, which I'll get to in a second. So I get better utilization by having fewer machines that are really big than I do from like a lot of machines that are smaller and talking to each other. And so the hourly rate here, you know, it might look a little daunting at $26 an hour, but this is going to be so efficient that it really isn't a big deal at all, and it actually is cheaper than running the R6 instances. So like I think a 1 terabyte R6i instance is about $8 an hour. The 1 terabyte here is $7 an hour, and if we put a bunch of R6s together, it would come up to higher than the cost of that one instance to get the same amount of memory and CPU capacity. So since these NVMe drives are there, they're not mounted by default, but it's not hard to do that. You have to format them and mount them. So like when we have a manual cluster set up, this is an example of how you could do that just inside the Ray cluster YAML. HDParm just forces the kernel to rescan the partition table, and then you format it in XFS or whatever you want. You make a /data directory, you mount that drive there, and then you change the ownership. In this case, EC2 user is just the default Amazon Linux user, but if you had Ubuntu or something else, that would just be a slightly different command, but you want the user to own it instead of root, so that when Ray processes that are running in user space, they can write to it and they don't have any issues there. So this is where that really comes in handy, because now when you start the Ray head node, you can pass this. You see in the middle of this, there's this system config for object spilling, and you can tell it, when you spill objects, I want you to write it to /data. And so what that's going to do is now it's going to write any spillage to that NVMe drive, which is really fast. And so if your cluster size is like with a lot of overhead, you might not run into this, but if you're trying to like squeeze out as much efficiency as you can on your instances, this helps, because eventually it'll start spilling to disk and you'll have to read some of that stuff back, and that'll help a lot. Another thing you can do is update what type of EBS storage you have attached to it, to the root disk. So you don't have to go too crazy here, but it sometimes writes things to the temp folder, or you may just need to read something. You can get a lot of IOPS, which are expensive to keep around for a long time, but when you just have a cluster that comes up and goes down within a number of hours, it's pretty negligible. So that's another thing we sometimes do. So metrics. So, I skipped a slide. There it is. Yeah, so here's an example. This is a 3-node cluster of those 4 terabyte X2I instances. They load data in parallel. So each worker is loading over 530 megabytes a second here. And And I've seen this peak over 1 gigabyte a second in some of the training runs I've done. And you remember it was about 18 megabytes a second in the default S3 config. So you have about a 30x speed up here just by having this disk available. And if you recall, it didn't waste any time to do that. It took about 20 minutes to populate all 6 months of data into that disk cache. So that was just a really quick step we had to do before spinning up the cluster. So this just saves tons of time, and that way all the EC2 time you're paying for is literally just training time. It's not spending time just loading and loading and loading data. So that's pretty fast. So here's just an example. I trained on 1 month of data just to get some numbers for this presentation. So all of these instances have 1 terabyte memory of each. So I put 2 of them together for 2 terabytes. So in this example, it took about 32 minutes to load all the data from S3 and train on it in the default example where it was using S3FS. But then moving to Lustre, that cut that in half, and we got a small reduction in the pure training time as well, because it's a little more efficient. So this was about 16 minutes. The X2 instances also cut the training time slightly, but it's pretty similar on a small data set. You get to bigger and bigger instances, or I'm sorry, data sets, that X2I comes in handy, as well as those NVMe drives. If you start spilling to disk, then it starts being more noticeable that those things are really helping you out. And in our real world in-house training on 6 months of data, it was taking around 9 to 10 hours at least to train on the full 6 months, and more than half of that was just loading data from S3, and it was expensive and kind of a waste. But and if something happened like in the middle of that and your cluster died, well, guess what? You got to start that all over again. So you end up just wasting money while you're developing this thing. Whereas your whole cluster can go down with this Lustre file system. It doesn't matter because that's decoupled from the instances, right? So you can have any number of machines pulling data out of that disk at the same time, and they don't affect each other, right? So that cut our training time down to around 4 hours, and that's 4 hours spent just crunching numbers in XGBoost. It's not really doing anything other than what it's supposed to. So looking at what does this actually cost? It sounds expensive, but it's really not expensive at all. So you have your Scratch file system. It's like 14 cents per gigabyte a month. So that whole almost 10 terabyte disk for the 5 hours we use, it's under $10. That EC2 time, that's obviously the most expensive. Each one of those is about $26 an hour, but we're not using them for super long, so it's $320. The provisioned IO, this is optional, but you could take it or leave it when you see how cheap it is. I mean, it's not a huge deal to throw that in there. So yeah, it's about roughly $350 for us to train this model on 6 months of data, and these are pretty good costs. If you're used to neural networks and GPU training and all this is like a drop in the bucket in your budget. But it's not. It's just it helps with developer productivity. The shortens the loop, and you can do a lot of stuff with this data at the same time because it's just loaded on this disk. So yeah, let's see, I've got 6 minutes left. So yeah, that's all I had. But I guess we have time for some questions if anybody had any. And this is a link to our Foresight Labs. This is like a little kind of a fun thing we put out there where we have a few models that people want to play with them. These specifically our team, our machine learning team puts these out. And so there's one of these you can choose for arrival runways, and you can pick random flights, and it'll show you the graphs of what it thinks. It'll do both ones that have already landed as well as ones that are in the air, so you can get real time. Where do I think this airplane's going to land, and what's happening with it? So. Yeah, this is a fun little thing we put out there. We use Streamlit, which is a really cool thing if you've never worked with a Python visualization app. But yeah, that's all I had. So.
Did you try out the LightGBM library as well?
So the question was, did we try LightGBM? And yeah, we did try LightGBM. So we had some older models running on LightGBM. We were pretty happy with the performance there. When I researched this particular one, I tried XGBoost, LightGBM, and CatBoost on the same data sets, and they were pretty similar, but XGBoost was the winner in most cases, so we just moved forward with that. But I think LightGBM also has a version that runs on Ray, so I think you can also scale that out as well. Yeah.
Yeah, I asked because we should have reduce the memory pressure relative to XGBoost.
Oh, really?
And
That's.
Ray supports that one as well. It's the parameter specs, the API is almost identical to XGBoost.
Oh, that's good to know. Maybe next time we reevaluate whether we're going to update it, we'll look into that because it would be nice to take that memory pressure off. But and at the end of the day, as you saw, like the memory's so cheap, it almost doesn't matter because like if I spent one day like like just moving it over, it would exceed the cost of the training. So, any other questions? Yep.
So when you were done with the training, so you were deleting the data from FX cluster, and then for the second thing you would load it back, and is that the model that
So you're asking if we delete it after training?
Yeah, so from a workflow point of view, like generally you will actually run your query multiple times, I guess, if that's what data scientists do. So will you leave the data into FX cluster every time?
No, you can leave it. You can leave it there. Like you could have an automated teardown as part of your cluster setup or teardown, but because that's decoupled, you can just leave it there, and you could do multiple trainings. You could try different hyperparameters. You could do like ray tuning or something like that, which we actually did that. So that's a good example when we're trying to hyperparameter tune it. We just left the data there and just run training cycles over and over again. So yeah, you can definitely do that.
Apologies if you already said it, but how many features are you using?
This model 263 is what we have currently. Yeah, and so yeah, it's a mix of where the plane is, how fast it's going, heading and destination origin, all these sorts of things. There's some features about the runway, like how long are all these runways, and so yeah. Mm-hmm. Yep.
Do you incorporate weather data into that at all?
We do, yeah. So not only the current weather conditions at the airport as well as forecasting. So we use, there's like the NBM, which is the National something model that I'm forgetting now. We also use the global forecast system in some systems since it's global and has some more data. But this one, we're only using the NBM forecast. Yep.
Did you evaluate using SageMaker training for this, or which already integrates with FSX?
So I think we did try SageMaker. Well, no, not for training. I don't think we did because we decided we wanted to use Ray, and it was just easier to set that cluster up ourselves exactly the way we wanted to, rather than use SageMaker. But we tried SageMaker out for like some of our inference. We host this model on NVIDIA Triton because it's like really efficient at throughput, and I think SageMaker supports that. So we kind of evaluated that as an option too. But yeah.
How did you come up with the configuration of the Ray cluster? Like, for example, how did you decide, okay, this workload or this training would require 5 nodes of, let's say, 32 GBs of RAM, each having a node of versus 10 nodes of 16 GBs of RAM?
Yeah. So he's asking how we decided to size this cluster the way we did and figure out like how much did we actually need. And the truth is it was trial and error. Like I have that slide that shows you how to figure it out, but at the time I didn't know how to do that. So I was just like trying to train it, and it would run out of memory. And I would give it another node and it would run out of memory. And I would watch like how much memory usage it was using until I kind of dialed it in. But then once I read more deeply in their docs and figured out how they figure out the memory pressure and I did the numbers, I was like, oh, well, now it actually kind of makes sense why it needed that much memory. So.
Experiments on smaller data set in order to get.
Yeah, so yeah, we did that and kind of extrapolated and said, well, this is probably about what we need. And then if it wasn't, then we'd add another node, or kind of like instead of trying 3 4 terabyte ones, maybe we try 5 3 terabyte ones, or some different configuration. But yeah.
I think we are
one
almost
more.
up on time. I've got 1 minute, but yeah, go ahead.
Is it possible, like, is there an API for the model where I can take the ADS-B data that I'm picking up with like a RTL SDR and pump it into the model?
No, because it requires like features that you would have to calculate that you don't have access to, but it is part of our, it's becoming part of our API, so it'll be exposed pretty soon. Like if you use the JSON APIs or the Firehose API, it's like starting to come through there. So.
Okay, I think we're up on time. Let's give Patrick another round of applause.
Thank you.